The multinomial theorem. What if we want to compute the powers of x plus y plus z, or u plus x plus y plus z instead of just x plus y? The same line of thinking will help, only the result will be a little more complicated to describe. Example 4.10. We have x plus y plus z to the cube equals to x to the cube plus y to the cube plus z to the cube plus 3x squared y plus 3x squared z plus 3y squared x plus 3y squared z plus 3z squared x plus 3z squared y plus 6xyz. Solution. We want to compute the product of x plus y plus z times x plus y plus z times x plus y plus z. To do this, we have to pick one member of each of the three sums, take their product. Do this in all 3 to the cube equals to 27 possible ways, then add the obtained 27 products. All the 27 products we obtain will be terms of degree 3. The only question is what the coefficient of these terms will be. Why is it, for example, that the right-hand side of 4.8 contains 3x squared y and 6xyz? Let us first examine how can one of our products be equals to x squared y. This happens when two of our three picks is an x and the third one is an y. There are three ways this can happen, as we can pick the single y from any of our three parentheses. Then we must pick the two x terms from the remaining three variables. Therefore, the coefficients of 3x squared y in x plus y plus z to the cube is indeed 3. Clearly, identical argument applies for all terms of degree 3 that contain one variable on the second power. There is only one way for one of our 27 products to be equal to x to the cube. Indeed, that happens if and only if we choose an x from each of our three parentheses. Therefore, the coefficient of x to the cube in x plus y plus z to the cube is 1, and the same is true for y cube and z cube. Finally, what about the term xyz? To get such a term, we have to choose an x from one of our three parentheses, which can be done in 3 ways. Then we have to choose a y from the remaining 2 parentheses, which can be done in 2 ways. At the end, we must pick z from the last parenthesis. Therefore, there are 6 ways we can obtain an xyz term, completing the proof. Just as in Theorem 3.21, we need a higher level of abstraction before we can state a general theorem along the lines of example 4.10. First of all, we want a theorem that works for any number of variables, not just the 3. Therefore, instead of calling our variables x, y, z, we will call them x1, x2, and so on until xk. The following definition generalizes the notion of binomial coefficients. Definition 4.11. Let n equals to the summations of ai summing with index I starting from 1 to k, where n and a1, a2, and so on until ak are non-negative integers. We define n choose a1, a2, a3, and so on until ak equals to n factorial divided by the product of a1 factorial, a2 factorial, and so on until ak factorial. The numbers n choose a1, a2, and so on until ak are called multinomial coefficients. The reader should verify that if k is equals to 2, then this definition reduces to that of binomial coefficients. Now we are in a position to state and prove the general theorem we have been working for. Theorem 4.12, Multinomial Theorem. For all non-negative integers n and k, the equality x1 plus x2 and so on plus xk to the n is equals to the summations of n choose a1, a2, and so on until ak times x1 to the a1 times x2 to the a2 and so on times xk to the ak, summing for all a1, a2, and so on until ak. So if the equality holds, that's the multinomial theorem. Here the sum is taken over all k tuples of non-negative integers a1, a2, and so on until ak such that n is equals to the summations of ai, summing with index I starting from 1 to k. Proof. We have to show that the term x1 to the a1, x2 to the a2, and so on times xk to the ak can be obtained in exactly n choose a1, a2, and so on until ak ways as a product of k variables, one from each parenthesis of x1 plus x2 plus and so on plus xk times until times the last term x1 plus x2 and so on plus until plus xk. To obtain such a term, we have to choose xi from exactly I parentheses for all I in k braces. Now let us take ai copies of xi for all I in k braces and order these n letters linearly. Theorem 3.5 shows that this can be done in exactly n choose a1, a2, a3, and so on to ak ways. On the other hand, each linear ordering P defines a natural way of choosing variables from the parentheses. Indeed, if the jth letter of P is xi, then from the jth parenthesis we choose xi. This way, our n choose a1, a2, and so on until ak linear ordering will produce exactly n choose a1, a2, and so on to ak terms that are equal to x1 to the a1 times x2 to the a2 and so on times xk to the ak. It is clear that this procedure establishes a bijection from the set of linear orderings of n letters, ai of which is equals to xi for all I in k parentheses until that of terms of x1 plus x2 and so on plus xk to the n that are equal to x1 to the a1 times x2 to the a2 and so on times xk to the ak. Therefore, the coefficient of x1 to the a1, x2 to the a2, and so on times xk to the ak in x1 plus x2 and so on plus xk to the n is precisely n choose a1, a2, and so on until ak. And the proof follows. There is a close connection between multinomial and binomial coefficients as explained by the following theorem. Theorem 4.13. For all non-negative integers n and a1, a2, and so on to ak such that n is equals to the summations of ai summing for all index I starting from 1 to k, the equality n choose a1, a2, and so on until ak is equals to n choose a1 times and so on times n minus a1 minus a2 and so on minus ai choose ai plus 1 and times and so on times the last term n minus a1 minus a2 and so on minus ak minus 1 choose ak holds. Note that n minus a1 minus a2 and so on minus ak minus 1 is equals to ak. So the last binomial coefficient on the right-hand side of 4.11 is equals to ak choose ak is equals to 1. Proof. The left-hand side counts all linear ordering of a multiset that consists of AI copies of the symbol xi. For all I in K braces, we show that the right-hand side counts the same object. Indeed, let us first choose the AI positions we place all our symbols xi, x1. This can be done in n choose a1 ways. Let us now choose the a2 positions where we place our symbols x2, as a1 positions are already taken. This can be done in n-a1 choose a2 ways. Then we can choose the a3 positions where we place our symbols x3. As a1 plus a2 positions are already taken, this can be done in n-a1 minus a2 choose a3 ways. Iterating this procedure, we will choose the positions of all symbols, and we see that the total number of possible outcomes is indeed the right-hand side of 4.11.